Right. Consider any planet. Let's say its mass is m and its radius is r. As I said, we consider planets to be uniform solid spheres as far as your syllabus is concerned. Assume there's a particle, okay, particle or an object just above the surface of the planet, okay, or you can say it is on the surface of the planet. Fine. Now we know from everyday experience that when you project something in the upward direction, it rises to a certain height and then falls back to the ground. Okay. Let's say the object's mass is small m. Ignore the atmosphere of the planet. Okay. So air resistance and all you'll ignore. Now, if you give the particle some velocity in this direction, okay, in a direction perpendicular to the surface of the planet. So basically in the vertically upward direction, you give it some velocity. Depending on how much velocity you give, the particle will rise to a certain height and then fall back. Usually in everyday life, they won't rise to such great heights where gravity will change. Okay. But if you give very, very high speeds, it is possible that they rise to very large heights also. Okay. Comparable to the radius of the planet. Fine. So let's say for one speed u or u1, it goes up to this distance. You give another speed u2 greater than u1, okay, then it will go to a distance greater than what it goes for u1 and then falls back to the planet and so on. Okay. So consider a situation like this. Assume the particle or the small object is given a speed of under root gm divided by 2 capital R. Okay, where capital M is the mass of the planet, capital R is the radius of the planet. So the particle is given this much speed in a direction away from the planet. Now, due to that speed, it will start moving forward. Okay, due to that velocity, it will start moving. And as it moves away from the planet, the gravitational force of the planet will slow down the object. So it will slow down and stop somewhere. Find out the maximum height. Find out the maximum height. Okay, see on paper it looks like a horizontal, on screen it looks like a horizontal distance, but relative to the planet that is a height. Okay, find out the maximum height to which the object rises above the surface of the planet. Solve this all of you. It is projected away from the planet with a speed under root gm by 2r. To what maximum height will it reach above the surface of the planet? Can one of you tell me the idea, the concept that you will apply? You are given speed at one position and you are asked what maximum distance it will go. Okay, tell me, can we use equations of kinematics or the formula for H max that we derived in motion in a straight line, that is u square by 2g? Can this formula be used here?
No, sir.
Why not?
Because as it gets closer, the gravitational force will become more and more.
Here we have to consider the possibility of variation of acceleration due to gravity as an object goes away from a planet. Now this u square by 2g is valid when g is uniform, when acceleration due to gravity is uniform. In the last class we discussed when the object goes to significantly large heights above the surface of a planet, gravity decreases. So we cannot use this formula here. Okay. So can one of you tell me an idea? How are you going to find out the maximum height to which the particle is going to move or rise? Aishwarya, any method you can think of?
So can we find the gravitational potential energy at that height?
Can you repeat? The first few words were not audible.
So like we can try finding the gravitational potential energy at that height.
And then?
And then find the difference from the initial potential energy.
What will difference in potential energy give you? Okay. Any other ideas, anyone? Actually, Aishwarya, you are quite close to the answer. You have to make use of potential energy. But when you talked about potential energy itself, it must have stuck to you that you can use mechanical energy conservation. Okay, Ui plus Ki is equal to Uf plus Kf. Fine. Let's just visualize this a little better. I'll take a bigger picture of the planet. The particle is projected exactly from the surface of the planet with a speed under root 2 gm by r. So to what maximum height is it going to rise above the surface of the planet? See, as it goes farther and farther as the object goes farther and farther from the planet, it becomes slower and slower, and at some distance it will stop. Okay, so the final velocity is 0. So you know initial velocity, you know final velocity. You need to find out to what extent it will move. Velocities and arrangements are related in mechanical energy conservation. Okay, and you know this object stops due to gravitational force of the planet. So gravitational force is a conservative force. So mechanical energy conservation is valid in this situation. So do this, all of you. Initial potential energy plus kinetic energy of the object should be equated to its final potential energy and kinetic energy. And again, I want one of you to tell me, can we use potential energy as, can we calculate potential energy as mgh? Can we use this formula here? Gravitational potential energy mgh is valid only when g is uniform. Okay, so for very small heights above the surface of Earth, you can use this. But we don't know to what height this object is going to rise. It can be a very large height. Okay, in fact, you can estimate it will be a very large height. You substitute the values of Earth. G is 20 by 3 into 10 power minus 11. G is a very small number, okay, in SI units. But mass of Earth, 6 into 10 power 24. That is a huge value. Divided by radius of Earth. Radius of Earth is 6.4 into 10 power 6. Still, this is going to be a very large value. Gm by r. Under root also is going to be a very large value. It's a very high speed. Okay. So with such high speeds, it will definitely rise to significant heights compared to the radius of Earth. So small g is not going to be uniform. You can't use equations of kinematics or h max is equal to u square by 2g. You can't use potential energy mgh also. You have to use the proper formula for gravitational potential energy between a solid sphere and a particle outside it. Okay, solve this problem, all of you. I'll give you 3 minutes. As the particle moves from, call the initial position A to the final position B, okay, apply mechanical energy conservation and derive to what maximum distance it will move. Okay, I got one answer as r by 3. Let us check. So we know the initial speed is under root gm by 2r. Fine. I asked you to revise the formula for potential energy between a solid sphere and a particle. Okay, hope you have done it. I'm using it directly. So we have to apply mechanical energy conservation here. Ui plus Ki is equal to Uf plus Kf. Initial potential energy between the solid sphere and this object. Okay, the object is just outside the solid sphere. So distance from the center to the object initially, okay, center of the sphere to the object initially is r. So gravitational potential energy initially will be minus g capital M small m divided by r. Next is kinetic energy. The planet is assumed to be at rest. Okay, we are looking at everything relative to the planet only. So planet's kinetic energy need not be considered. The object's kinetic energy is half small m multiplied with the square of its velocity. Its velocity was root gm by 2r. If you square it, it becomes g capital M by 2r. Okay. So initial potential energy plus kinetic energy of the system should be equal to final potential energy. Finally, let's assume it goes to a height h above the surface of the planet. Okay. Then if the particle is here finally, it is still outside the sphere only. And when the particle is outside the sphere, the total potential energy between the sphere and this particle depends on this distance from the center to the particle, which now becomes r plus h. Okay. So final potential energy is minus gmm by r plus h. And there the particle is assumed to come to rest. Okay, it rises, but as it rises, it slows down and stops somewhere. That is the maximum height. Okay. What is left is just simplification of this equation. On the left hand side, you have minus gmm by r plus 1/4 of gmm by r. Minus 1 plus 1 by 4 is minus 3 by 4. So left hand side becomes minus 3 by 4 gmm by r. And the right hand side is minus gmm by r plus h. Okay, minus gmms cancel. Cross multiply. You get 3 times of r plus h is 4r. So 3r plus 3h is 4r. Send the 3r that side. You get 3h is equal to r. That means h is equal to r by 3. Good. So it rises to a height of 1/3 the radius of the planet, which is a huge height. Okay. Is this clear to all of you? Any doubts in this? Fine. So when projected with a speed of under root gm by 2r from the surface of the planet, the object rises to a height of r by 3, 1/3 the radius of the planet. Now, if you increase the speed of projection, the height to which it rises also will increase. Because if you are giving more speed, means you are giving it more energy, then the height to which the object rises also will increase. Now you can keep on increasing this speed. Okay, you can keep on increasing this speed and keep on increasing the height to which it rises. And for one particular speed, it will go to infinite height also. Okay, means it will go away from the planet forever. It will never come back. That speed, that minimum speed with which you should project an object, okay, the minimum speed with which an object must be projected such that it escapes to infinity is called the escape velocity from the surface of the planet, or escape speed. Include direction, it becomes velocity. Okay, let us derive an expression for that. Escape velocity from the surface of a planet. Okay. Consider a planet of mass m, radius r, and assume there's an object here. The object has to be projected with some speed. Okay, that speed is what we need to derive this time. So with what speed should the object be projected? Okay, or to be more precise, with what minimum speed should the object be projected from the surface of the planet such that it escapes to infinity? Means the final position is at infinite distance from the planet. Okay, so since you are finding out the minimum speed with which it should be projected, then after reaching infinity, the particle can come to rest. If you give more speed than necessary, then after reaching infinity also it will keep moving. Means its velocity will never become zero. Okay, if you give just the bare minimum required velocity, then after going to infinity it will stop. Okay. Fine. Apply mechanical energy conservation and derive the expression for initial speed, all of you. This time we know the final speed and we know the final separation. We know initial separation as well as final separation. So arrangements are known to us. Final speed is known to us. Initial speed is what we need to calculate or derive. Okay, do this all of you. Derive the expression for escape velocity. I'll give you all 2 minutes. I want everyone to answer. Okay. in the previous problem, you have seen how mechanical energy conservation can be applied. Do the same here and derive an expression for the initial velocity. I'll just adjust the diagram a little bit. Solve quickly. Good. So applying mechanical energy conservation, initial potential energy is minus gmm by r. Initial kinetic energy is half mu square. U is what we need to derive. Final potential energy. When an object goes off to infinity, at infinite separation, we assume potential energy to be zero. In fact, under that assumption itself, this formula is valid in the first place. Okay. So final potential energy at infinity is zero. And we are just projecting it with the minimum required initial velocity. So after reaching infinity, it comes to rest. Final kinetic energy is also zero. Just simplify this equation. You get U is equal to under root 2 gm by r. So if an object is projected with that speed from the surface of a planet, it will escape to infinity. Okay. And it is also important to note that this speed or this velocity can be given in any direction, not just in a direction perpendicular to the planet, not just this way. You may project it with that velocity, with that speed in this direction. You can even project it parallel to the surface of the planet. Irrespective of the direction of projection, the object will never come back to the planet if you give it this much speed. Okay. If you substitute mass of Earth and radius of Earth, then you get escape velocity on Earth. It will be under root 2. G is 20 by 3 into 10 power minus 11. Mass of Earth approximately 6 into 10 power 24 divided by the radius of Earth 6.4 into 10 power 6. And these are all in SI units, so the velocity will come out in SI units. And you simplify it, it will be 11.2 kilometers per second. Okay. This is a very, very high speed. Nothing that is on Earth has this speed. No object on Earth has this speed. Okay. If it has, it will escape from the Earth, provided there is no other disturbance. Okay. Obviously, that is also an ideal case. In a real life situation, if you throw something, then definitely atmosphere or air resistance will be there. Fine. In the absence of air resistance and all, this is the case. Okay. But still, it's a very large speed, 11.2 kilometers per second. This is not per hour or something. Okay. Now, just like we had questions where I asked you to calculate acceleration due to gravity on other planets based on their mass radius, you can be asked escape velocity on the surface of other planets. Escape velocity on the surface of Earth is 11.2 kilometers per second. So this is basically under root 2g mass of Earth divided by radius of Earth. So they can tell you that the mass of another planet is 10 times the mass of Earth, radius is so and so number of times. Find out escape velocity on that planet. Easy only, you can do it. Okay. Let's solve some more problems. This formula under root 2 gm by r is when you project the object from the surface of the planet. You can be asked to calculate escape velocity from some other points also. Okay. Let's try some problems like that. Again, consider a planet of mass m, radius r. Assume there's an object already at a height r above the surface of the planet. Somewhere here. With what minimum speed should the object be projected from here such that it escapes to infinity? Derive this quickly, all of you. So basically what you're deriving is escape velocity from a height r above a planet. Do this, all of you. 2 minutes. Yeah. Okay, I got answers from 3 of you. All 3 of you have given the correct answer. The procedure is the same. You need the minimum speed such that you can send it to infinity. So ui plus ki is equal to uf plus kf. Initial potential energy is minus gmm by this distance, which is 2r. Okay, that's all. That's the only difference in the equation. So initial potential energy minus gmm by 2r plus initial kinetic energy half mu square is equal to final potential energy plus final kinetic energy. Simple. This time the 2's will get cancelled. You will get the escape velocity as under root gm by r. So escape velocity can vary depending on where you are projecting it from. Okay. So the formula under root 2 gm by r is valid when the when the mass is projected from the surface of the planet. Keep that point in mind. Okay. You can be asked such questions in reverse also. Now, if you are giving some initial velocity and projecting the particle, it is going to a certain distance. How do they ask you the question in reverse? An object is released from a certain height. With what speed will it hit the planet? Such questions can be asked. Okay, let's solve one like that. Let's say there's an object which is initially at a height. Okay, the height itself is 2r above the planet. Okay. Object mass is small m. It is released from rest. So it is dropped. Now, you know, due to the Earth's or the planet's gravity, it will gain velocity as it approaches the planet, and it will hit the planet's surface with some velocity, with a significant velocity actually. Derive that velocity. Solve it quickly. The initial height above the surface of planet is 2r. Okay, based on that you solve. Okay, I got 3 different answers so far. Under root 4 gm by 3r, under root gm by r, and under root 4 gm by r. Let's see. Pawan, can you unmute?
Yes, sir.
Uh, what idea have you applied?
Sir, mechanical energy.
Mechanical energy conservation. Fine. So tell me, how much is the initial potential energy between the planet and the particle?
Sir, gm by 2r. gmm by 2r.
See, I repeatedly told you that the height above the surface is 2r. Height అనేది ఎప్పుడు కూడా surface నుంచి తీసుకుంటారు, center నుంచి కాదు. But for potential energy, you need distance from the center. Okay. And also, I'm telling this to all of you. If you forget the minus sign, energy conservation based problems will go wrong. The formula for gravitational potential energy will always have a minus sign if you take infinity as the reference. Okay. So initial potential energy between the planet and the mass is minus gmm by, what's the distance from the center of planet to the mass? 3r. From surface it is 2r, from the center it will be 3r. Okay. The particle is released from rest, so initial kinetic energy is 0. Planet's kinetic energy is anyway considered to be 0. Finally, like at the instant when we want to find out the speed of the object, it is just on the surface of the planet. So final potential energy will be minus gmm by r. And final kinetic energy is what we need actually, half m v square, assuming v is the speed of the object just before it hits the surface. After hitting the surface, we can't say what will happen. Okay, because once it hits the surface, you have to apply concepts of collisions. We don't know what kind of collision is, all that. You don't even have to bother about all that. Okay. So just before hitting the surface is what we are considering. Okay. Minus GMM by R, send it this side, becomes plus. So 1 minus 1 by 3. 2 by 3 GMM by R is equal to half mv square. Okay. Aishwarya, good, your answer is correct. You get V as under root 4 GM by 3R. Okay. Next. Okay, fine. So basically using mechanical energy conservation, you can relate speeds between 2 points and the change in the arrangement. Basically how far the object goes and all you can find out. In fact, you can even be asked questions like this. Questions where they say a tunnel is dug through the planet. Okay, let's say imagine a tunnel like this. It's a very narrow tunnel actually. You cannot see also. It is along the diameter. The tunnel will be covered by mass. Okay, you can't see the tunnel. But imagine there's a tunnel like this through the center of the planet. Okay, passing through the center of the planet. Fine. It's not like we have cut the planet in half. We just drilled a hole along the diameter of the planet. Okay, imaginary situation only. Then they can ask you if a particle is just released here. Okay, the planet's gravity will pull it in. You know, solid sphere creates a field inside also. If it creates a field, then the particle will experience a force. It will experience, if it experiences a force, it will gain velocity. So they may ask you, with what speed will it reach the center of the planet and so on. Okay, let's solve one problem like this. Let's see how many of you can actually do this. Not related to speed, but related to field. Okay, I'm just giving you a slight hint. Assume a tunnel is drilled through the planet. It's a very narrow tunnel. Okay, why it is important to know whether it's a narrow tunnel or not is because if it's just a narrow tunnel that you are digging through the planet, you are not effectively removing much mass. Okay, so it is still almost a complete solid sphere. Okay, you can ignore the mass that is missing. So imagine a tunnel like this. Planet's mass is capital M, radius is R. Okay. Now what they did is they placed a chain in this tunnel. A long chain was inserted in this tunnel. Okay. Or it was lowered into this tunnel. So you can think of it like this. Now, how long a chain shall we consider? Let's say half the radius of the planet. Okay. Diagram is ridiculous. Leave it. Let's say a chain like this is lowered into the tunnel. Chain's mass is small m and its length, obviously, as you can see, is half the radius of the planet. One of you tell me, will the planet exert a force on the chain or not? Will the planet exert a force on the chain or not?
Yes, sir.
Definitely. Solid sphere creates a gravitational field everywhere. It creates gravitational field outside the sphere. It creates gravitational field inside the sphere also. And if there is field and a mass is present, that mass will experience a force. Okay. You have to calculate the total force acting on the chain. Derive the force exerted by the planet on the chain. Okay, think carefully and solve. It's not a particle. Okay, it's an elongated object. The chain is an elongated object, and its length is significant also. It is half the radius of the planet. Okay, so think carefully and solve. I'll give you all 5 minutes. Try. Have I given all the necessary information? Mass of the chain is given. Length of the chain is given. Yes. Answer will be in terms of capital G, capital M, small m, and of course R. Okay. Okay, listen all of you. Let us do some qualitative analysis also. Before we actually solve this, suppose you had options and you could choose from the options. There are some things you can do. Now, if the entire mass m was exactly on the surface of the planet, what would the force have been? Or how much would the force have been? If the mass m was exactly on the surface, okay, completely on the surface, how much would the force on it have been?
GM by R square.
Gmm by r square. Okay. Now what is happening is the mass m, instead of being kept only on the surface, is being distributed like this. It is being sent into the surface. Now, when you go into the surface of a planet, does gravity become stronger or weaker? We had discussed in the last class. Where is gravity of a planet the strongest? In acceleration due to gravity. At the surface, it is the strongest. Okay. So when all the mass is at the surface, it experiences a force m into g naught. G naught is gravity on the surface. But when some of the mass is sent inside, or if the mass is distributed like this, like a chain into the planet, okay, chain, what do you call, dropped into a planet, okay, or lowered into a planet, then only at the surface the gravity, the acceleration due to gravity will be g naught. At other points, it will be lesser than g naught. And if acceleration due to gravity is less, the gravitational pull will be less. So the overall force acting on the chain when it is lowered into the tunnel, it should be less than gmm by r square. The answer should be less than gmm by r square. Okay, because only on the topmost particle of the chain, the acceleration due to gravity is g naught. On other points of the chain, which are inside the planet, gravity will be lesser. Okay, so compared to the force experienced when the chain is completely on the surface, the force experienced when it is lowered into the tunnel should be lesser. Okay. Now let's see how to do the calculation. Can any of you tell me an idea how to actually find out the force between the chain and this planet? Pawan, what logic did you use?
Sir, F is equals to M into
F is equal to m into a. Okay. How much is a?
Sir E.
E. How much is E?
GMX by R cube.
Okay. You use the gravitation formula for gravitational field inside a solid sphere. Good. And how much is X?
R by 2.
Why did you take X as R by 2? Why don't you take 3R by 4? Why don't you take R? Why did you choose only this point, R by 2? There is chain here also, there is chain here also, there is chain here also. Then why only take this point? Why only consider field at that point? See, you have to think all this, no? By now you should have got, I'm telling this to all of you, not just to Pawan. I'm telling this to all of you. the gravitational field of a solid sphere varies from point to point. How can you take field at one point and apply it to the entire mass? Okay, it should not do that. Fine. So this is an obvious case of integration. So what we'll do is we'll consider an element of this chain first. I'll have to take an, okay, let it be, we'll adjust here itself. Consider an element, or fine, just for clarity, let me use a plain diagram, no colors. Okay. On different elements of the chain, the acceleration due to gravity is different, or the gravitational field of the planet is different. So what we are going to do is consider a random distance x and call the length of the element as dx. On that element, we'll first find out how much force will act. Integrate that, you will get the total force on the wire. Simple. Okay. Now this element is inside the solid sphere. When the particle is inside the solid sphere, you can't treat the solid sphere as a single particle and use particle formula. Okay. So little bit of what Pawan suggested is correct. To find force, you need to do mass multiplied with the field. So this small element will experience a small amount of force, which is its mass multiplied with the field at a distance x from the center of a solid sphere. So that becomes d small m. D small m is the mass of the element of the chain. And field created there by the solid sphere is G capital M x by r cube. Okay, that's the force experienced by this element. And you need to integrate this force to get the total force on the wire. I told you this, I mean, we had talked about this at the beginning of the chapter. Forces are vector quantities. When integrating vectors, you should first see if all the vectors that you're going to integrate are in the same direction or not. Now, the solid sphere will always create a field towards its center. Okay, so be it this, whether it's this element or any other element, the force on the elements is going to act towards the center itself. All elements will experience force in the same direction. So you can integrate the magnitudes of force, that is enough. Okay, if vectors are all in the same direction, the magnitude of the resultant is just the sum of individual magnitudes. Okay, integrating vectors or integrating forces is like summing up vectors. So you should take care of the direction also. Fine. All these forces are going to be in the same direction. Therefore, the total force will be an integration of this. Okay. Now, from element to element of the chain, x is a variable. So you'll have to express dm in terms of dx. And you know how to express dm in terms of dx. dm is equal to lambda dx. Linear mass distribution. Chain is a linear mass distribution. So total mass by total length multiplied with dx. Total mass by total length is lambda. So you can write dm as 2 small m by r into dx. Put that there. So the force becomes integral gm x by r cube into 2 small m dx divided by r. Okay. So 2g capital M small m by r power 4 will stay out of the integral. What will be left inside the integral? X is x dx. X dx integral is x square by 2. And in this, we have to substitute the limits now. What is the starting value of x? For the first element, the starting value of x is r by 2. And for the last element, the final value of x is r. So r by 2 to r. Okay. Now this 2 and this 2 can be cancelled first. What remains is gmm by r power 4. And when you substitute the limits, r square minus r by 2 whole square is r square by 4. 1 minus 1 by 4 is 3 by 4. The answer is 3gmm by 4r square. And as expected, it's less than gmm by r square. It's just 3/4 of it. Okay, hope this is clear to all of you. This is one way to solve it, by integrating. Okay. Of course, this is the best way to solve it. Best means mathematically, most appropriate way to solve it, I would say. But if you are very comfortable with mathematics, no, you can think of other ideas also like this. Listen, the chain is completely inside the solid sphere. The problem here is that the gravitational field produced by the solid sphere is different at different points. How much field does the solid sphere produce on its surface? We are talking about field, it will be gm by r square. How much field does it produce at its center? Gm x by r cube. No, gm into r by 2 divided by r cube, gm by 2r square is the field at the lower end of the chain. I should not say center, lower end of the chain. That's the field. Now we know that gravitational field inside the solid sphere is given by the formula gm x divided by r cube. The field is proportional to distance. When y is proportional to x, the average value of y will be the average value of x. I mean, I should not say will be the average value of x. You can write average value as gm by r cube into x initial plus x final divided by 2. Now, why am I talking about average field? If you know average field, you can find out the force directly. The problem here was that the field was varying from point to point. If you know the average value, then you can use that average value directly. Okay. And since the field is proportional to distance, okay, when direct proportionality is there or when a linear variation is there, average value is always the midpoint of the extreme values. Now, initial x is r by 2, final x is r. Initial r by 2, final is r. What's the mid value of half and 1 3/4? Okay, so this becomes 3r by 4. So the average gravitational field on the chain due to the sphere is 3 gm by 4r square. And if you know that this is the average gravitational field, multiplying that with the mass of the chain will give you the average force that it experiences. And that is what we want. That's all. You could have solved it this way also. Okay, this process eliminates the necessity of integration. Anyway, a slightly difficult question only, but it's not unsolvable for your level also. You can solve. And this question was previous JEE advanced question. Not exactly the same. I think they gave chain length to be d. Instead of giving r by 2 half of the radius, they gave some other length. But the idea was the same. You had to use the same idea. Okay. Anyway, this has nothing to do with potential energy and all. It's a force-based question. Let it be. So we discussed how to do energy conservation based problems between a planet and an object, right? Okay. So if an object or a certain mass is just released from a certain height, released means released from rest, from a certain height above a planet, you know it is going to fall straight down onto the planet. And as it falls, it will gain velocity. We can even find out with what velocity it is going to strike the planet. Okay. Instead of releasing it from rest, let's consider a tangential path around the planet. Just an imaginary path, okay? I'm not saying the object actually moves along that path. Imagine a circle like this around the planet. What if you give this object some velocity tangential to this circle? Okay, let's say you give it some velocity like this. Can one of you tell me or any of you tell me, what are the possible things that could happen with the object or to the object? We are giving it some speed or velocity in the tangential direction and releasing it. What could happen?
Here the particle will execute circular motion.
Okay. That is one possibility. Okay. The particle may move in a circle around the particle, or the object may move in a circle around the planet. Okay. It can orbit the planet. In fact, that is what happens with our moon and the satellites, artificial satellites. That is what they do for one particular speed, which is called as the orbital speed. Okay, we'll derive that. The object will go around the planet in circles. It will keep on revolving around the planet unless it is disturbed by something else. That's one possibility. What if the speed is less than that?
So the object may fall into one.
Correct. If the speed is less than that, the object cannot stay on that circle. See, gravitational force of the planet will be there. Fine. So that force will be pulling the object towards the center of the planet. To withstand that force and stay in a circle, certain amount of speed will be needed. If that much speed is not there, what will happen? The object will fall onto the surface of the planet. Okay. So this is what happens if the speed is less than the orbital speed. Fine. What if the speed is more than orbital speed? More than that required to stay in a circle. See, you may not know the exact answer. I'm not asking you general knowledge based questions. I'm asking you to just share your ideas. What do you think will happen if the speed is more than orbital speed?
Or it will go out of the orbit and just stop orbiting.
It will go out of the orbit, that's fine. And you said it won't orbit anymore. Means it will go off to infinity.
No, it depends on the speed also, sir. So it'll just stop after a point if it's not enough.
It will stop. Why will it stop? If it
Sir,
stops, then
because
the gravity of the planet will pull it in. If it stops anywhere, it will fall down to the planet. Isn't it? Any distance, if you release an object, it will get attracted to the planet.
So the particle will go away from the planet.
So you are saying it will go off to infinity.
Yes, sir.
So, okay, let's consider that answer. If speed is greater than this orbital speed, she's saying it goes off to infinity. Now we derived escape velocity today itself, the speed required to send it off to infinity. Okay, and we derived escape velocity from a height also, like this question. So do you think orbital velocity is the escape velocity? Because you are saying any velocity greater than orbital velocity, the object will not come back. Means you are saying, you are indirectly saying orbital velocity is the escape velocity. Okay, we'll see. But that is not correct actually. Okay, what happens is, see, with orbital speed, it goes around in a circle. If you give speed greater than orbital speed, but less than escape speed will be a different value. We'll do all those calculations, you'll understand. Okay, in fact, you yourself can do. Anyway, so orbital speed is different, escape speed is different. So if the speed is anything between these two, between orbital speed and escape speed, what happens is the object still orbits the planet, but not in a circle. Okay, it goes around in an elliptical path like this. Anyway, I'm not drawing it properly, but it goes around in an elliptical path if speed is greater than the orbital speed. So it will go out of the circle. Again, it will come closer this way. Okay, so it follows an elliptical path. So go on increasing the speed, the ellipse size will go on increasing. And when you give escape speed, the object is never going to come back. Okay, so if you give escape speed in a direction like this, then what will happen? It will turn a little bit due to the planet's gravity, but then it will go off to infinity. It won't orbit the planet. Okay, fine. So let's first derive an expression for orbital speed. The speed which is necessary for an object to stay in a circular orbit around the planet. And based on what factor shall we derive? Assume the mass of the object that is orbiting to be m, and distance from the center of the planet all the way to the object, let it be x. Okay, you can split or you can express x as radius plus some height above the surface also, but let's take the total distance as x and solve. Okay, so what we need is an expression for orbital speed. Can any of you tell me how to derive this? You need not have studied this chapter. Basically, I'm asking you what is the speed needed to stay in a circle? How do we solve such problems?
So we can find out the centripetal force and equate it to
Correct, correct.
gravity.
You use the equation for centripetal force. What is the force which acts on this mass after it is projected? The gravitational force of the planet, the gravitational pull of the planet. And that force will be towards the center of the planet. So gravitational force will be acting inwards. Under the influence of gravitational force itself, it moves in a circle, like our moon revolving around the Earth. Okay, it happens due to Earth's gravity itself. Okay. How much is the gravitational force between the planet and that object? The object is outside the planet, so the planet can be considered as a point mass placed at its center. And the distance between capital M and small m is x. So the force becomes g mm by x square. And this itself is the centripetal force on the object. So you equate it to the centripetal force, mv square divided by r. R is the radius of the circle in which the object moves, and the radius of the circle in which this object moves is x itself. So cancel one x, small m gets cancelled. You get v naught square is gm by x. Therefore, v naught, the orbital speed, is under root gm by x. Okay. Important formula. This is a concept, a separate concept actually. Orbital speed of a satellite. So depending on the height where you want to place the satellite, you will have to give it a particular speed. So basically what happens during satellite launches is, so it will be predetermined where the satellite is to be placed. Okay. So the height above the Earth where you want the satellite to be placed will be known to you. If you know height, radius of Earth is already known, means x is known to you. So what happens is, see how are satellites launched? Rocket will first take the satellite to the desired height. Okay, rocket by using its fuel takes the satellite to the desired height, and after taking it to that desired height, it gives the satellite, whatever machine is there inside the rocket, it gives the satellite the necessary amount of orbital speed and releases it. Once the satellite is released with that amount of speed, it will keep revolving around the planet forever. Unless it collides with something, slows down and falls down to the planet. Okay, it keeps revolving around the planet at that height itself. So that is what happens in satellite launches. Okay. So at whichever height you want to place the satellite, based on that height, you need to provide sufficient amount of energy to the rocket. First for the rocket and the satellite to go to that height, and then the rocket has to give the required kinetic energy to the satellite. It has to give the required speed to the satellite and release it in that orbit. And then the satellite will keep revolving in that orbit. Okay, so this is the formula for orbital velocity or orbital speed of a satellite. So it depends on the mass of the planet around which you want to release the satellite. Okay, and it depends on the radius of the orbit in which you want the satellite to revolve. You can also express this as under root gm by X is the total distance from the center of the planet to the satellite. You can also write it as radius of the planet plus the height above the surface of the planet. Okay. Now, at that height, usually we place satellites in space. Okay. What is space? Space is basically a region outside the Earth's atmosphere. Fine. Up to a certain height above the Earth, you have gases. Okay, you have the atmosphere. Beyond that, you can call it space. Okay. So when a satellite is placed in orbit, there is no atmosphere there. So there is no air resistance there. Fine. The only significant force which the satellite experiences is the gravitational force of the planet. Fine. There may be gravitational force from other planets, the sun, our moon, and such entities, but those forces will be negligible. The only significant, okay, force that the satellite experiences is the gravitational force of the Earth. Now you can see that that force is directed towards the center of the Earth. It is perpendicular to velocity of the satellite. Not just at this instant, at any instant, the velocity of the satellite will be tangential to the path, and the gravitational force will be radial to the path or perpendicular to the path like this. The angle between them is always 90 degrees. Now, if force is perpendicular to velocity, what does such a force do? It only changes the direction of velocity. It doesn't change the magnitude. Therefore, the satellite goes around the planet with uniform speed. Magnitude of velocity, that is speed, does not change. Direction has to keep changing. And if an object moves in a circle with uniform speed, you call it uniform circular motion. Therefore, satellite executes uniform circular motion. Why does this matter? Uniform circular motion has something called a time period of revolution. The satellite always takes the same amount of time to complete one revolution around the Earth. And that is also important. You will require some satellites to rotate along with the Earth. Now, you know Earth takes 24 hours to complete a rotation. Then you will have to set the satellite in such an orbit where it will also have a time period of 24 hours so that the Earth's rotation and the satellite motion will be in sync with each other, synchronized. Okay, such satellites are called geostationary satellites. We'll discuss about them. So the time period of revolution of a satellite around the planet is also important. Basically, what are satellites used for? Communication, weather forecasting, such things. You need to, basically, you're keeping an eye on the planet, or you are allowing communication, receiving signals from somewhere on the planet and sending them to some other place on the planet. Fine. Either observing the planet or for communication. These are what satellites are used for. And for both purposes, you need to know the specific position of the satellite, or you need to place the satellite in a specific position relative to the planet. Okay. So the time period of revolution of satellite is also important. So we know, or we have just discussed, that it executes uniform circular motion. Now, to complete a circle, the distance that the satellite has to travel is the circumference of the circle, 2 pi x. And the speed with which the satellite travels is the orbital speed, which is under root gm by x. We just derived that. And if you know distance and speed, you can tell the time it takes to complete one revolution. Therefore, time period of revolution of a satellite. Total circle circumference, that is 2 pi x, divided by the speed with which the satellite revolves, that's the orbital speed. Simplify this, it becomes 2 pi x divided by root gm by x. So it becomes 2 pi under root x cube divided by gm. This is the time period of revolution of a satellite around a planet. And the time taken by the satellite to complete a revolution around the planet depends on the radius in which you place the satellite and, of course, the mass of the planet. Now, usually we are interested in satellites around the Earth. Okay, so mass is always mass of the Earth. Then time period is proportional to square root of x cube, or you can say x power 3 by 2. So time period is proportional to x power 3 by 2, where x is the radius of the orbit in which the satellite revolves. And you square on both sides, you can also say t square is proportional to x cube. Square of time period of revolution of a satellite is proportional to cube of radius of revolution of the satellite. Again, ratio based questions on this are very common. They can give you two satellites in two different orbits, like two different radii, and ask you what is the ratio of their time periods of revolution, such questions. Okay. I hope this is clear to all of you. Satellite can revolve around a planet with the help of the gravitational force exerted by the planet. That gravitational force provides the required centripetal force. So just write equate gravitational force to centripetal force. You will get the expression for orbital speed. You can even tell time period of revolution. And these same ideas we will use, or you will be using, in atomic structure also. You all must be knowing, having a basic idea of what is present in an atom. Electrons revolve around the nucleus. Okay. Electron is a negatively charged particle. The nucleus of an atom, which is at the center of the atom, is a positively charged center. Now, you know positive and negative attract. Okay. Unlike charges, opposite charges attract. So that attractive force acting on the electron, okay, which is electrostatic in nature. It's not a gravitational force. It is electrostatic force. The electrostatic force between nucleus and electron helps the electron revolve around the nucleus. So you'll be doing almost these same calculations with electrostatic force in atoms. Okay. So yeah, orbital speed, time period of revolution. Fine. Let's just discuss one common point. Now we say, or you might have heard, that there is no gravity in space. How many of you have heard this? Only one? Okay, two. Fine, fine. This is actually wrong. Okay, there is gravity everywhere. In fact, for gravity or the gravitational force of Earth to become zero, you should go to very, very large distances from the Earth. Okay, infinite distance. Or if you go there, also some other planet's gravity may be acting. Sun's gravity will be there. Gravity is there. Okay. Then why do we say there's no gravity in space? Or some of you might have seen astronauts in the International Space Station. Okay. International Space Station is basically one, what do you say, one room. Okay. Very sophisticated room, which scientists have placed in the space. Okay. International Space Station. Basically what they do is, it's like a, okay, it's like a hotel. So when you travel to a new place, what do? You stay in a hotel and you explore around. So if they want to explore space, no, they'll go stay there in the International Space Station and do whatever exploration they want to do. Now, you might have seen videos of astronauts floating around in, or flying around in the International Space Station as if there's no gravity, as if they're never going to fall down. Okay. Sorry. Okay. So those of you who have not raised hands, tell me, if there is gravity in space, like you said, you never heard that there's no gravity in space. So I am thinking you believe there is gravity in space. Okay, those of you who didn't raise hands, you believe there's gravity in space. If there's gravity in space, why are astronauts flying around in the International Space Station? Why are they not falling down? Anyone? Even those of you who raised hands, if you know, you can tell. I'll give you a minute. Think about it. Fine, that is an interesting explanation. She is saying that maybe the International Space Station is exactly at the neutral point between Earth and Moon. If it is exactly at the neutral point, then Earth's gravity, Moon's gravity cancel. But no, that is not where the International Space Station is. Just a moment. I'll find out how far the International Space Station is from the Earth. From the Earth, the Moon is around 4 lakh kilometers. Neutral point, it splits the line joining them in the ratio 9:1. So it should be about 3.6 lakh kilometers. Okay, I'll quickly look up how far the International Space Station is. I'm sure it won't be that far. Okay. International Space Station orbit height is just 408 kilometers. That's all. It is very close to the Earth's surface. Definitely, it is outside the Earth's atmosphere. Can any of you tell me up to what height Earth's atmosphere extends? I forgot. You must have studied, no? Layers of atmosphere, stratosphere, troposphere, those things.
Well, 10,000, 8,000 or something like that kilometers.
How can it be that much? Okay. International law defines the edge of the atmosphere for legal purposes to be at an altitude of 100 kilometers. Okay. Altitude of 100 kilometers is called the Karman line. Okay. Above the Earth's surface. After that, there is no atmosphere, or even if it's there, it's not significant. Okay, the density is not significant. Fine. Recently, they have launched space exploration also. Not just astronauts, even common people can go to space now. I mean, they just did some trials. Two companies, I think Blue Origin was one of them, Amazon person. And the other one was, okay, SpaceX or Virgin Galactic, one of them. So they took people to a height of, I think, around 80 to 100 kilometers. They just made them cross this line. Once you cross this height, you are officially in space. Okay, so they just took them there and brought them back also. Okay, this is all like latest technology. Usually, rockets which are used to launch satellites, they take the satellite to a certain height, launch the satellite, and the rocket is lost. Okay, it falls back to the Earth actually. Once the rocket loses its fuel, it can't propel itself. Earth's gravity will pull it back. Rocket will fall back to the Earth. But when the rocket falls back to the Earth, what happens is it will have to enter into the Earth's atmosphere. Earth's atmosphere actually protects the Earth. Okay. Earth's atmosphere is what? A dense layer of gases. Okay. It's a dense collection of gases. So when the rocket, whose fuel is exhausted, falls back to the Earth and enters into the Earth's atmosphere, now it's falling from a great height. It enters into the atmosphere with a very high speed. When the rocket enters the atmosphere with such high speeds, air resistance, which is basically friction, generates such a high amount of heat that the rocket disintegrates in the atmosphere itself. It gets burnt off in the atmosphere. Okay. That way, the Earth's atmosphere protects the Earth. In fact, it protects us from asteroids also. Very recently, few days back, only one asteroid got burnt in that Earth's atmosphere. Okay, many times we are protected from asteroid collisions by our atmosphere. Of course, some asteroids do manage to strike the Earth also. It has happened in the past. Okay, maybe not during your or my lifetime, but in maybe millions, billions of years ago, it has happened. In fact, they say there's one theory that dinosaurs became extinct because an asteroid hit Earth. That time there was such a lot of heat generated or some disturbance generated that entire what do you call? The species itself got eliminated. Okay, but usually what happens when an asteroid enters into the Earth's atmosphere? Asteroids will be moving at very high speeds. When they enter into the Earth's atmosphere, The air resistance generates such high amounts of heat that the asteroid disintegrates in the atmosphere itself. Small bits will fall here and there, and you know Earth's surface is 75% water. Okay, so most likely the rocket that disintegrates or the asteroid that disintegrates is most likely going to fall in the ocean itself. Okay, sometimes they fall on the land also. People do find pieces of meteors and all here and there. Okay, sometimes it lands on like well-populated areas also, but they are just small bits of the rocket. It doesn't cause significant harm. Anyway, what was I asking? Yeah, why do astronauts appear to fly in the International Space Station or in space? Okay. Anyway, this class has become too long. Let it be. But you all find out the answer. We'll discuss this in the next class. Okay. And next class, we'll discuss a little bit more about satellite motion, energy, potential energy, kinetic energy of a satellite. And after that, there is something called Kepler's laws of planetary motion. Next class, we'll finish this chapter. Okay. Thank you all. We'll continue in the next class. But find out the answer to that. Why astronauts appear to be flying around in the International Space Station. Okay.